Hello, and welcome to the section 1.2. We're going to talk about exponents and radicals today. So let's start with exponential notation. If a is any real number and n is a positive integer, then the nth power of a is a to the n, which is the same thing as a times a times a n times. The number a is called the base, and n is called the exponent. Let's do an example here of what this actually looks like. I know you all have probably worked with them, but it's good to do examples anyway. So 3 to the 5th is the same thing as 243. Here we would say that 3 is the base, 5 is the exponent. Similar, but instead of using an integer base, we have a 1/2 for a base to the 6th power. So again, 1/2 is the base, 6 is the exponent, equal to 1/64. Now let's talk about 0 and negative exponents. If a is not equal to 0 and a real number, and n is a positive integer, then a to the 0 power is equal to 1, and a to the negative n is the same thing as 1/a to the positive n. So this is a very common expression, a to the 0 equals 1. Note that a is non-zero. This is important because 0 to the 0 is not actually equal to 1. There's a process to finding a 0 to a 0. A to the negative n, the negative, what this does is it tells us to move the entire term that the exponent is connected to from the numerator to the denominator or from the denominator to the numerator. So in this case, this is the same thing as saying a to the negative n divided by 1. So a to the negative n is already in the numerator. This negative on the exponent is saying move it to the denominator. So then we change the sign, 1/a to the n. I want you to try one. A, find 123,456,789 to the 0th power, and B, 2 to the negative 3rd. Next, we're going to talk about the rules for exponents. Let a be a non-zero real number, and n and m be positive integers. We're going to talk about the laws of exponents here. One, a to the m times a to the n is equal to a to the m plus n. We have 2 to the 3rd, 2 to the 4th, equal to 2 to the 7th. All you have to do is add the exponents. 3 plus 4 is 7. To multiply two powers of the same base, all you do is add the exponent. Note that a is the same base here. The exponents are probably different. M and n aren't necessarily the same. 2, a to the m divided by a to the n equal to a to the m minus n. Add it, 3 to the 4th divided by 3 squared is equal to squared. 4 minus 2 is equal. Divide two powers of the same base, subtract the exponents. A to the m, the nth power, equal to the a, the m times n. 4 squared, 3rd power, equals 4 to the 6th. To raise a power to a new power, multiply the exponents. Or ab to the nth power is equal to a to the n, b to the n. 2 times 3 to the 4th is equal to 2 to the 4th times 3 to the 4th. To raise a product to a power, raise each factor to the power. 5. A over b to the nth power equal to a to the n divided by b to the n. 2 divided by 3 to the 4th power is equal to 2 to the 4th divided by 3 to the 4th. Raise a quotient to a power, raise both the numerator and the denominator to the power. Now I want to make a note here. With this particular one, 4 goes on the entire numerator. So if you had a product in the numerator, that 4 is going to be on the entire product. So it would revert to something that looks like this. So suppose we had AB in the numerator here, the 4 would be attached to the A times B. And then you would use this property to sort of distribute the power to each factor individually. So you have to make a note that the power goes on the entire numerator and the entire denominator. A over b to the negative nth power is the same thing as b over a to the n. As we saw before, when you have a negative power, it changes the position from the numerator to the denominator. So we can use the rule from 5 to apply this negative n to the a and the b, and it will flip their positions, and then you can use this rule again to pull the n out to be on the quotient again. 2 over 3 to the negative 4th power is going to equal to 3 over 2 to the 4th power. To raise a fraction to a negative power, invert the fraction and change the sign of the power. Now this also has the implication that if you want to create a negative power, you can do so. So because we have equality, remember equality holds both directions. 3 halves to the 4th is the same thing as 2/3 to the negative 4th. So if it suits us to have a negative power, we can write it in a way that gives us a negative power. A to the negative m over b to the negative n is equal to b to the n divided by a to the m. 2 to the negative 4th over 3 to the negative 5th is equal to 3 to the 5th over 2 to the 4th. Move a number raised to a power from the numerator to the denominator, or from the denominator to the numerator, change the sign of the power. I think that's illustrated well here. If you have a negative power, we can move it to the numerator and we change the sign from a negative to a positive. Again, because equality holds both directions, we can also move the 3 to the 5th power, even if it's a positive, we can move it into the denominator and negate the power. So then we would have a 3 to the negative 5. Usually we only do this when it suits us. Want to make a note? A number has an understood exponent of 1 unless otherwise specified. So for instance, x. X has a first power. We don't have to write the 1 here. It's understood that there is a power 1 there. We know that it's not 0 from one of the previous slides, because any number, any non-zero base, the 0th power is equal to 1. So x to the 0 power is not x. It would be equal to 1. X to the first power is x. We're saying that there is one x here. It also has an understood coefficient of 1. It says a similar thing. We have 1x here. Okay, let's prove a couple of these because I think the proofs are pretty important. When we go through this class, I'm going to try to show you why things are true so that you get a better understanding of them as a concept instead of just trying to memorize everything. So for instance, we're going to prove 1, 3, and 4. I think the rest of them pretty much follow from those 3. So here, a to the m, remember that a to the m means a times a times a m times. So we have a to the m here, and there's m of these. There's m total a's listed here. Multiplied by, now we look at a to the n, a times a times a times a, and there's n of them here. So I have m a's here and I have n a's here. If I drop my parentheses, then we can look at them all in a line, a string of a's together. And how many are there? Well, there's m here and n here, so in total, we have a to the m plus n. 3, a to the n to the mth power. Here what we're saying is, we list out a to the n m times. A to the n, n, a to the n, a to the n. How many of these do I have? I have m of them. So if I list out each one of these individually, there's n here. That's this guy. There's n here as well. And here as well. And there's n here as well. So I have n here, n here, n here, and n here. In total, I have m groups. So there's m groups of n. Which, if you remember your multiplication from elementary school, that's basically the definition of multiplication. So this becomes a to the n times m, or m times n. AB, get the power. So here we list out AB n times, all multiplied. AB, AB, AB. Now there's n total here. Now what I'm going to do is I'm going to rearrange my multiplication. Remember, multiplication all happens at the same time. So I'm going to rearrange them because b times a is the same thing as a times b. It's commutative. Multiplication is commutative. So we can rearrange it so that all of our a's are first. And how many do I have? And all my b's are second. And how many b's do I have? Also n. So if I now group these, then I'm looking at a to the n here times b to the n here. So we end up with the proof for. Let's do an example. A, x to the third times x squared. So we have the same base, x. So we can write it as x to some power, where the power is the sum of these two numbers, exponent. B, x over 2, the negative 2. Now this negative 2 is going to get distributed to both of these factors, the numerator and the denominator. So we can look at this as x to the negative 2 over 2 to the negative 2. Now, remember, we have a negative exponent, which means change the position of this thing, whatever this negative exponent is attached to. Well, the negative exponent is attached to the 2, so this will move to the numerator. And this x to the negative 2 we have a negative exponent as well, and this negative exponent is attached to x, so this moves to the and we're done. Try one. Simplify. Y squared x over z to the negative 3. Okay, so when I say simplify here, what I'm referring to is simply get rid of your negative exponents. Make sure that you have a single fraction, not a compound fraction. You have a single fraction and no negative exponents. Next thing we're going to talk about is scientific notation. It doesn't come up too often, but it comes up often enough that a positive number x is said to be in scientific notation if it is expressed as follows: x equals a times 10 to the n, where a is greater than or equal to 1 and strictly less than 10, and n is an integer. I want you to notice that n is an integer means that n has the possibility of being negative. Now, the sign in the scientific notation is going to be described by which way we move a decimal. Let me show you what I mean here. Example. Suppose we want to put the value 0.00156 in scientific notation. Now, if we consider this our a, this is actually our x value, but we want to get an a value associated with this. Now, when we multiply by 10, all we're doing is moving the decimal. So what we want to do is we need an a that's associated with this number, so we need to move the decimal to a point where a is between 1 and 10, strictly less than 10, but greater than or equal to 1. And then we'll figure out what our n is. Here, we need to move the decimal 3 spots. So our n is actually going to have the value 3. And our a is going to be 1.56. Because now we just need to multiply by 10 a few times, or 1/10, depending on the exponent of 10, to get back to this. So the value of our n is 3, but since we moved to the right, our exponent is negative. So we get that this is our x value, then x will equal 1.56 times 10 to the negative 3 value. Because we moved 3 units to the right. Because we moved right, we have a negative. 3 comes from the fact that we moved 3 spots over. Decimal move. Move the decimal until it is directly to the right of the first non-zero digit. So we would move 3 units in this case. The exponent is the number of times the decimal moved. The sign of the exponent is determined by which way the decimal is moved. If you move to the right, then your exponent is going to be negative. If you move to the left, your exponent is going to be positive. As we note here, we moved right, thus we have a negative exponent, and we moved beyond the first digit. That's how many places you need. Let's now talk about radicals. Note here, this is called the square root symbol. We say square root of a is equal to b if and only if b squared is equal to a, and b is greater than 0. So when we say that we're looking for the square root of a number a, we're looking for the number whose square is a. I'm going to repeat that. When we're looking for the square root of a, we're looking for the number whose square is equal to a. Example. Square root of 16, of course, equal to 4. So square root of 16 is the number whose square is equal to 16. So the square root of 16 is 4 because 4 squared is equal to 16. Right one? Square root of 9 over 4. Definition of the nth root. If n is any positive integer, then the principal nth root of a is defined as follows. The nth root of a is equal to b, if and only if b to the n is equal to a. If n is even, then a must be greater than or equal to 0, and b must be greater than or equal to 0. So this definition actually follows from the square root, as it should, because 2 is just a positive integer. This is the general case of the square root. So when we're looking for the nth root of a, we're looking for the number when taken to the power n gives us a. So the nth root of a is equal to b if and only if b to the nth power gives me a. Now I want to note here that this n is called the index. It's the index of the radical, or index of the root. And this plays a key role, as we'll see when we get into the properties. Do an example first. So a, cube root of negative 8, b, square root of negative 64. First, the cube root of negative 8 is actually defined. You might look at this and say, it doesn't look like it's defined because it's a negative number. Remember, we have an odd number, we have an odd index here. So when we're looking for an odd radical of a number a, b to an odd power can be negative. If b is negative and we take it to an odd power, then that will give us a negative number. For instance, negative 1. Negative 1 to the third is equal to negative 1. Negative 1 times negative 1 times negative 1, there's 3 negatives, so we get a negative value. So this actually turns out to be negative 2. Negative 2 times negative 2 times negative 2 gives us negative 8. Now when you have an even index, and when the index is not, when the index isn't here, it's understood to be 2. So we have an even index here. Our index is 2. Then this number needs to be positive. Otherwise, we start to tread into the complex numbers. I don't know if y'all have ever covered complex numbers with the imaginary number I. That's what we're talking about in this case. So up to this point in the class, we would say that this is undefined. Properties of nth roots. Got the property here. And example. 1. The nth root of a times b is equal to nth root of a times the nth root. Now this is assumed that n is a positive integer and a and b are real numbers. So what we're saying here is that if we have the nth root of a product, we can split the product into separate nth roots. Cube root of negative 8 times 27 is equal to the cube root of negative 8, which we already know is negative 2, and the cube root of 27, which is 3. 2. The nth root of a quotient. We can split that into separate nth roots as well. Fourth root 16 over 81 is equal to fourth root of 16 divided by the fourth root of 81. The mth root of the nth root of a is equal to the m nth root of a. This will make sense in the next part of this section. We have the square root of the cube root of 64. This is the same thing as the sixth root, 64. Remember, this is an understood 2. If it's not written, if the index is not here, then it's understood to be 2. So in this case, our m is 2 and our n is 3. So we would multiply them to 6. The nth root of a to the n is equal to a if n is odd. So here, the cube root of -7 to the third power is equal to -7. Now we have to specify whether n is even or odd in this case, because even powers are slightly different. They work a little bit different because of the negatives. Remember, an odd number, negative numbers being multiplied together gives us a negative number. But an even number of negatives does not. So we actually get that the nth root of a to the n is the absolute value of n when n is even. Here, and I'm going to illustrate this. So, when we take -2 to the fourth power, we are multiplying a negative 4 times. So we actually get a positive number. So this would be the same thing as saying the fourth root of 16. But now this fourth root doesn't understand that we had a negative number here. So when we see that the fourth root of a positive number, it's assumed to be positive. And it is positive. It gives us just 2. Which is the same thing as absolute value of 2. If we do this a little bit differently, and write it by using the property. Let's do an example. A, the cube root of x to the 5th. So when you see something like this, what you want to do is you want to break it down using the properties. In this case, because we have the cube root, we're using property 4 and property 1. Now notice that n and n don't match. Our index and our exponent don't match in our problem. Our exponent is 5 and our index is 3. But we can break this up into x squared times x cubed. This is where we're going to use property 1. We have an nth root of a product. Our a in our case is x to the third, and our b is x squared. X to the third, x squared, ab. So multiplication here. So that we could break this up into cube root of x cubed times cube root of x squared. Now we have an odd n to the same exact power. our exponent matches our index. That would be the rule 4. And our n in our problem is equal to 3. So we get that this just becomes x times the cube root of x squared. Now there's nothing we can do about this problem because there's not enough exponents to actually reduce. Our index is larger than our exponent. So we don't have enough x's to be able to pull one out. Try one. Simplify this one. Fourth root x to the 10th divided to 7. I want you to simplify it in much the same way we did the example. I also need to make this note because it happens all too often. Many of you watching this video will fall into this category as well. Try to get ahead of this. Note that the nth root of a plus b is not equal to the nth root of a plus the nth root of b. This happens way too often. Right? This is a very, very, very common mistake. These two things are not equal. Notice that there's no rule that describes anything that looks like this, where you have a sum underneath the radical, because it won't simplify. Right? There is no sum under a radical, only multiplications and divisions. So this, do not do this. Do not make these two things equal. So the next thing that we're going to talk about are rational exponents. Now, rational exponents are going to sort of combine the ideas. They combine the ideas of exponents and radicals together. Start with the definition. For any rational exponent, m over n, in lowest terms, where m and n are integers and n is greater than 0, we define a to the m over nth power is equal to the nth root of a quantity to the m, or a to the m over n is equal to the nth root of the quantity of a to the mth power. If n is even, then we require that a is greater than or equal to 0. Now recall that when we have a rational number, so m over n is rational, automatically implies that m and n are integers. But we also want m over n to be in lowest terms. Now, that's not the most important thing, but being in lowest terms is helpful. Note that we can write it this way or this way, and we can see that by using a rule of exponents. So a to the m over n is equal to a to the m times 1 over n, which is the same thing as a to the m 1 over n, which would then become the nth root of a to the m. Or we can write it as a to the 1 over n to the n times n equal to a to the 1 over n to the mth power, which is equal to the mth power of the nth root of 8. Let's go ahead and do an example here, what this looks like. A to the 4 thirds, a to the 7 thirds, divided by a to the 2 thirds. So here we have a to the 4 thirds times a to the 7 thirds. Notice that we have the same base. Since we have the same base, we can just add the exponents. We have 4 over 3 plus 7 over 3. Since we have the same denominator, that doesn't change. We just add the numerators. We get 11. And then we have a to the 2 thirds in the denominator. And of course, for similar reasoning, We have a common base, a and a to the 11 thirds divided by a to the 2 thirds. We just subtract the exponents, which will give us a to the 9 thirds equal to a to the third power. Now I want you to try one also. Write the expression with rational exponents as an expression with a single base. So similar to what I just did in this example, I want you to write it as an expression with a single base. Like we have x to the 3/5 times x to the 8/5 over x to the. So in this next part, we're going to talk about rationalizing the denominator. So recall, the nth root of a to the n is equal to a, or the nth root of a to the n is equal to the absolute value of a, depending on what n is. In this case, it's n is odd, and in this case, n is even. So here, what we're going to talk about is trying to get rid of the radical. That's the whole idea behind rationalizing a denominator, is to get rid of all the radicals if you can. Now, we have this property, which is 4 and 5 from our previous properties in the radicals, where if the index matches the exponent, then we can write it as an expression without a radical. So the key is to get the index and the exponent to match. Now, also notice that we're talking about rationalizing a denominator, not the numerator. So if the numerator is not rational, that's totally fine. A couple of examples like this. So if we have, say, 1 over the square root of x, how would we rationalize this? Well, we can multiply by a form of 1. Remember, when you multiply a number by 1, because 1 is the multiplicative identity, it doesn't change the value of the problem. So we are always welcome to multiply a number by 1. It's not always necessary, but in this case, that's what we're going to do. So we're going to multiply by the square root of x over the square root of x. And when we do this, remember the index is 2, and right now our exponent is 1. So we have an index of 2 and an exponent of 1. But when we multiply these straight across, we get the square root of x divided by the square root of x squared. Now we have an exponent of 2 and an index of 2. And these two will cancel using this particular property. Now I will also note here that we haven't talked about this yet, so if you don't understand this, it's okay. But because we have the square root of x, the domain of x is going to be greater than or equal to 0. And because it's 1 over the square root of x, we actually know that the domain is going to be greater than 0. X is greater than 0. So when we write this, we would use this property, and we get square root of x over the absolute value of x. But because x is always greater than 0, we can also write this as just the square root of x over x. Because if x is greater than 0, then the absolute value of x is equal to x. Same thing. Another example, this one's going to be a little bit trickier. We also want to rationalize the denominator of this particular problem. 4 over the cube root of x. So I want to rationalize this. Well, right now I have the cube root of x. Now I have an exponent of 1 here, but I have an index of 3. So maybe pause the video and try to figure out what you need to multiply by in order to get this to become a rational denominator, to rationalize the denominator. So what we're going to do again is multiply by a form of 1, because again, multiplying by 1 does not change the value of the problem. But I'm not going to multiply by the cube root of x. I'm going to multiply by the cube root of x squared. Top and bottom. Now remember, again, we're multiplying by 1, so it won't change the value. But notice here that I have an exponent of 1, and I need it to be an exponent of 3 to match my index. So this 1, when I multiply it here, will give me, will add to this 2, and we'll get an exponent. So we end up with 4 times the cube root of x squared, and in the denominator, we end up with the cube root of x times x squared. This comes from one of the properties where if you have a multiplication of two numbers with the same base or with the same index, then you can include them in the same indexed radical. So now when I do x times x squared, I get x cubed, which will give me 4 cube root of x squared on top, change, and then the cube root of x cubed on bottom. Now my exponent matches my index. So we take the cube root of x cubed, and I get x from this property here when n is odd. And then I'm done. I have a rational number here, and that's all we were looking for. I want you to try one now. Rationalize the denominator. X over 5th root of x to the 7th. This one's a bit trickier, but I'm confident that if you understand this particular example, you'll get it. This is actually going to mix the example, this example, with this example. So use this example and this example to solve this problem. That's going to be it for today. I will see you all in the next lecture.